Sir, engineering class for unit 5. Today we will see two things under unit 5. One is low pressure measurement and another one high pressure measurement. So you please take out your notebook. The agenda of today's class. First thing I want to cover high pressure measurement. Second one low pressure measurement. Okay? Are you ready for this? Hasnan?
Yes, sir.
Yeah. Let us start with first one. So we all know that the conductivity of a compressible fluid will get changes if its surrounding pressure gets changes. This is the principle behind high pressure measurement. So what we will do is we use a setup, a conducting metal. In this particular case, we use a conducting metal made up of gold. Okay. So what we will do is this we keep in a chamber. This we keep in a chamber. It is hanging. The conductor is hanging in this chamber, and the surrounding of this conductor is filled with kerosene. Filled with kerosene liquid, right? And from this end, high pressure is applied. High pressure input. Okay. So because of this high pressure gas, what happen is the conductivity of this particular metal gets changes, and which is the indication of our high pressure. So here, as the case of RTD, remember in the case of RTD, we are using this equation. Resistance changes because of increase in temperature is given by this formula, delta T into alpha, right? This delta T is change in temperature, and this R naught is temperature at 0 degree, and this R1 is because of change in temperature from 0 degree C to any value, and alpha is nothing but coefficient of uh, thermal conductivity. So this particular equation is actually used in order to track the change in temperature information in terms of change in resistance. The same concept can be extended to track the information about the pressure, right? Using this particular setup. Just see this thing. Resistance at, okay, there is a mistake in this. This is R1 and this is R naught. So this R naught is nothing but resistance at 1 atmospheric pressure, and these B is nothing but pressure coefficient, and delta P is nothing but pressure gauge. Is it clear? Pressure gauge information. This is nothing but P1 minus P naught. Delta P is nothing but P1 minus P naught. So initially, suppose the pressure of this particular chamber is P naught. So because of that, the resistance absorbed of this particular conductor is R naught. Now when pressure is applied, the resistance changes from R naught to R1 because of pressure changing from P0 to P1. Hope it is clear to everybody. Hasnain,
Yes, sir.
yeah, can you please brief what information I have given just now?
In high pressure measurement, gold is kept in kerosene filled tank
Mm-hmm.
and pressure is applied from one side.
Mm-hmm.
Uh, Change in pressure can be calculated from R1 equals to R naught into 1 plus delta P into alpha.
Here I am using the word conductivity changes. How is the connection between this and resistance? We all know that conductance is nothing but reverse of resistance. When
Yes, sir.
resistance changes, conductivity also accordingly changes, right? So don't get
Yep.
confused. When somebody use the word conductivity, somebody use the word resistivity, it all interrelated words, inversely proportional. Hope it is clear to everybody. Simple thing which we need to keep in mind here is, as that of RTD, is delta P, y axis is delta R. So we are going to get relation like this. In case of RTD, x axis was delta T and y axis is delta R. And in this particular case, x axis changes from delta T to delta P. Instead of temperature, here it is pressure, whereas y axis in both the cases remains same for high pressure measurement. So hope it is clear to everybody. See here, I'm just reading the text which is written in this PPT. A sensor mechanism used to measure extremely high pressure. Make use of the fact that this is the principle. Electrical resistance of a particular temperature conductor changes if it is compressed by an applied external pressure. This is the principle. But this is not used for low pressure. However, it is used for very, very high pressure. Such sensors are called as bulk compression gauges, right? So this bulk compression pressure sensor can work up to 1.5 10 to the power 6 psi of pressure. So it works on this particular principle. The resistance and change in pressure can be varied by this linear relation. This is like y is equal to mx plus c kind of equation, where this R0 is the resistance at reference pressure and R1 is because of applied pressure. Delta P we can write as P1 minus P2. So there is a figure over here. If suppose this is not clear, you can make use of this figure, right? Here you see pressure connection. This is actually sensor, and in the surrounding kerosene oil is available, and this is the terminal from where the resistance information can be taken to a bridge, right? We are not bothered about the rest of the thing of this particular setup. So here what happens is, in order to trap the change in resistance information, here what we will do is we make use of a Wheatstone bridge kind of stuff, right? In which one of the arm is this one. This is one of the arm, right? Hope it is clear to everybody.
Yes, sir.
Okay, this is Wheatstone bridge. So this is about high pressure measurement. Now I'm moving to low pressure measurement. We have seen that absolute pressure measurement can be calculated using this formula, right? Absolute pressure is given by this formula. Atmospheric pressure plus or minus gauge pressure, right? So for low pressure measurement, we use this formula. Absolute pressure is equal to atmospheric pressure minus gauge pressure. Please make a note of it. Hope it is clear to everybody.
Yes, sir.
Low pressure, sorry, high pressure and medium pressure. Absolute pressure is given by the formula atmospheric pressure plus gauge pressure. Whereas low pressure is given by the formula absolute pressure is equal to atmospheric pressure minus gauge pressure, because it is below atmospheric pressure. Its range is below atmospheric pressure. So the first one under this particular case is made on the principle of thermal conductivity. Just now we have seen thermal conductivity. Thermal conductivity of a gas can get changes if its pressure gets changes. The same principle is extended for the measurement of low pressure. But here in this particular case, the special design gauge need to be used. The setup is also different. So, but principle will remains the same. Let us suppose that this particular section is nothing but your Pirani gauge section. Usually low pressure is called as vacuum pressure. So what happens is the density of gas, here we are terming the principle like this: the density of gas available in a chamber of Pirani gauge gets increases if its pressure increases. That results in increase of the conductivity. So here the links are like this: if gas density is increases, pressure increases, conductivity increases. But we need to move in this way. If pressure increases, gas density increases, then finally what happened? Its ability to conduct increases. Hope it is clear to everybody.
Yes, sir.
Understand in this way: if pressure of the real gas increases, then its gas density increases, which make its conductivity of heat to increase. That we can try with the help of this particular setup. So that explanation is written over here. So this is called as Pirani gauge, which is just similar to that of our high pressure measurement, but setup is different. Now, this is just extension of that. So we all know that when conductivity increases, its temperature increases. So forget about it. When when conductivity increases, the resistance decreases. That we can measure with the help of this Wheatstone bridge, and it is used for low pressure measurement in the range low vacuum to ultra low vacuum. It's not high, it is ultra low. I'll just make a change: low vacuum to ultra low vacuum pressure. Hope it is clear to everybody. Hasnain.
Yes, sir.
Yeah. Next method of measuring low pressure is with the help of gauge called as Knudsen gauge. Knudsen gauge. Here what happens is, in a chamber we let the electron to emit, right, which is getting bombarded with the applied input pressure. Because of this bombardment, positive ions releases. फिर से बताता हूँ मैं. We are having a setup in which we are emitting electron. Input is first input. Input one is emission of electron. What is second input? This is second input. Low pressure. When this low pressure gas molecules are bombarded with this electron, then it results in this. This is output. What is the result? release of positive ions. Hope it is clear to everybody. अपने नोटबुक में लिख लो ये 3 points.
Yes, sir.
Please make a note of these 3 points. When electrons are bombarded with the gas molecules, it results in release of positive ion, which we try to measure and correlate in terms of low pressure measurement. So these two are input. This is input 1, this is input 2, and this is our output. एक बार फिर लिख देता हूं मैं आपको. So here inputs are two things. One is electrons, another one
Low
gas,
pressure.
low pressure gas molecules. So this is our Knudsen gauge. What is the output? Positive ions, right? Positive ions. Hope it is clear to everybody.
Yes, sir.
Huh. We try to measure this positive ion using this collector. This is actually a setup. We are providing a biasing operation with the help of which electrons are emitted in this particular chamber, and from this we allow the gas to get in. So these gas molecules are actually collided with this electron and result in release of positive ions. We are having a setup which is having capability to trap the positive ions, and that can be indicated on this particular meter, right? So here the sensitivity of this particular setup is it releases 100 milliamps of current with every increase in 1 torr of pressure. Hope it is clear to everybody. Yes, no, हसनैन.
Yes, sir.
हाँ, इधर देख लो, मैं पढ़ रहा हूँ आपको. It is also used for the measurement of same as that of our Pirani gauge. They sense pressure indirectly by measuring the electrical ions produced when the gas is bombarded with electron. Third point, thermionic emission generate electron. So this electron generation method is because of thermionic emission. We are not going into that thing. Which collide with gas atoms and generate positive ion, which I have mentioned over here. This electron is getting bombarded with these low pressure gas molecules and generating or releasing positive ions. What we are doing is we are providing a setup which measures the release of these positive ions and try to relate this with in terms of applied input pressure. The ions are attracted by suitably biased electrode. We have electrode over here. This is positive ion collector anode. Okay. So the current in the collector is directly proportional to rate of ionization, which is a function of pressure in the system. So this is the equation which is used in order to write the information on the display about pressure. IP divided by HES. This is constant quantity and this is varying and getting from the meter. Hope it is clear to everybody.
Yes, sir.
Okay. The last thing. What is time now? 1 second.
10:34.
Okay, I can continue this. This is the last setup which is there in our syllabus to measure low pressure. Mclead gauge. It is also used for low pressure measurement. It is a slow method of measurement of low pressure, but it is very efficient. Efficiency is good, but method is slow. Okay. So it is used for low. The silent feature of this Mclead gauge can be these 3 points in addition to these points. First point is it is again used for vacuum or low pressure measurement. Its efficiency is good, but it is slow method of measurement. So can I proceed?
Yes, sir.
Yeah. The other name of Mclead gauge is compression gauge. Because here what we are doing is we are trying to compress low pressure gas and resulting in high pressure gas. See, the concept is very simple. Low pressure gas is applied to this particular setup. This particular setup is changing low pressure gas into high pressure. And we have the Boyle's law, which states that the product of pressure and volume remains the same. Hope it is clear to everybody.
Yes, sir.
This is before compression multiplied with volume, and this is after compression multiplied with volume. So if suppose pressure changes, automatically volume changes. अगर pressure आप बढ़ा रहे हैं, the volume gets down. In this particular case, the pressure is low, volume is high. What we will do is we try to move or transform pressure information into volume information and do measurement, because without having a sophisticated mechanism, it is comparatively difficult to measure low pressure. So what technique we use in this Mclead gauge is we try to transform low pressure into high pressure and use Boyle's law in order to trap that information. Hope it is clear to everybody. Please acknowledge.
Yes, sir.
Yeah. Other silent features. Range is 10 to the power minus 6 star. It is invented by Mr. Mclead. There is some more name, I have not written that. But just observe the date, the year in which this invention happens. 1874. Very old. It is based on Boyle's law. What is Boyle's law saying? By compressing a known volume of low pressure gas to a higher pressure, what happened? Initial pressure can be calculated by measuring the resultant volume and pressure. Resultant volume is P2, sorry, V2, and resultant pressure is P2. Hope it is clear to everybody.
Yes, sir.
Huh. Very simple. I am proceeding. So we have this setup. What we will do is we have a setup in which three sections are available. So movable reservoir is available, with the help of which we try to move this mercury in and out. Initially, we release the mercury from this three setup and let the known pressure to come in. Then what happens is, in order to transform this low pressure into high pressure, we move this reservoir up and accordingly push the mercury level up. The funda is we actually wanted to increase P1 from P2 so that the volume decreases from V1 to V2. Hope it is clear to everybody. Yes, no.
Yes, sir.
Huh. We need to see even this also. This is important. You may be getting a problem based upon this thing. Okay. Bismillahirrahmanirrahim. Let V1 is the initial volume of the bulb and P1 is the unknown pressure, and P2 is pressure after compression, and V2 is the volume of the gas bulb after compression. According to Boyle's law, we can write P1 is P1 P2 product is equal to P2 V2 product, right? So here the area of the bulb is A and the difference between the height, this height and this height is H. Then the volume which is decreases can be given by this formula. This is actually small a into H. And the pressure which is increased from P1 to P2 is given by this formula. P1 plus this height, increase in pressure. Okay. So if we substitute the increase in pressure from P2, P1 to P1 plus H in this equation, above equation, in place of P2, write on P1 plus H, and in place of V2 volume. V2 volume is nothing but area into height, A into H. We can get the value of P1 pressure as small a h square divided by, actually this is like this, P1 into V1 is equal to P1 plus H into A into H. Just expand this, you will get AH square divided by V1 minus AH. So here the denominator, this value in comparison to this volume, remember I told you P1 is small pressure whereas V1 is high volume. So this high volume in comparison to this low volume is very less. So we can neglect this. AH is
Yes,
nothing but V2, right? We can neglect this. So we can approximately write AH square divided by V1. Therefore, the trap pressure can be written as AH square divided by V1. If a problem comes on this, you can answer. So this much I have covered all the topics of transducer subject from unit 1 to unit 5. Not even single topic is left.